Hello everyone, today we will be solving question number 35 from GATE 2020 chemistry paper. The question is the experimental magnetic moment 3.4 Bohr magnetron of a hydrated salt of europium 3 plus at 27 degrees Celsius is significantly different from the calculated value. The difference is due to the options given are option number A population of electrons at higher J levels via thermal excitation, option number B strong ligand field splitting of f orbitals, option number C strong spin orbit coupling, and option number D pairing of electrons in f orbitals. So in this question they have asked that the mu calculated, that is the calculated magnetic moment value for europium 3 plus is having a high difference than the experimental magnetic moment for europium 3 plus. So what is the cause for this difference in magnetic moment values? So we know that magnetic moment consists of spin component and orbital. So because of spin angular momentum and orbital angular momentum of an electron, we get spin magnetic moment and orbital magnetic moment. The spin magnetic moment, the spin only value is given by mu SO is equal to root over 4s into s plus 1, where s is the spin quantum number and equals to, since each electron is having a spin of half. So if there are n number of unpaired electrons present, then the s value is equal to n by 2, and from there the mu spin only value comes as root over n into n plus 2 Bohr magnetron. So if there is any unpaired electron, then spin magnetic moment will be there. And for 4D and 5D transition elements, that is for lanthanides and actinides, they are having high spin orbit coupling, because of which spin are paired and they also have orbital contribution in their magnetic moment. So for europium, the electron configuration for europium is xenon 4f7 and 6s2. Okay, now they are asking for europium 3 plus. That means 3 electrons will be gone and it will be a 4f6 complex. Now as for lanthanides and actinides, they are having high spin orbit coupling. So the electrons will be spin paired. So f orbital, there are 7 f orbitals, 1, 2, 3, 4, 5, 6 and 7. So all of them will be spin paired, and therefore number of unpaired electrons will be 0. Therefore the calculated magnetic moment for europium 3 plus is 0, whereas experimentally we are getting a magnetic moment value of 3.4 Bohr magnetron. So for most of the lanthanides, the spin orbit coupling constant is high, but there are two exceptions. One is europium 3 plus and the other one is samarium 3 plus. So generally for the other lanthanides, the spin orbit coupling constant value is approximately around 800 centimeter inverse, whereas for these two, The spin orbit coupling constant is around 300 centimeter inverse, which is close to kBt. kBt is the Boltzmann constant. So, since the spin orbit coupling constant value is uh, comparable with the kBt value, therefore, thermal excitation can take place at room temperature and hence, so the ground state for europium 3 plus is 7F0, but because of this thermal excitation, the electrons can go to the excited rotational levels, okay, where the electrons, all the electrons will not be spin and there will be presence of some unpaired electrons. So because of this comparable energy with kBt, thermal excitation can take place in the case of europium and samarium 3 plus, as a result of which it will electrons are getting uh, are traveling to higher rotational levels, as a result of which we are getting unpaired electrons at that level, and hence the magnetic moment is not equal to zero. So therefore, in this case, in the question that the experimental magnetic moment of hydrated salt of europium 3 plus is different from the calculated value, the correct option for this will be population of electrons at higher J levels via thermal excitation. So the other options which are given are strong ligand field splitting of f orbitals. That is true for f orbitals, but that has nothing to do with this option. The option number C is strong spin orbit coupling. Strong spin orbit coupling is observed for all the other lanthanides except for samarium 3 plus and europium 3 plus. So this won't be the option. And option number D is pairing of electrons in f orbitals. Because of high spin orbit coupling constant, electrons are paired in f orbital, but the magnetic moment which we are observing, this is because of the strong, like less value of spin orbit coupling constant. So this option is also not correct. So option number A is the correct answer for question number 35. That is, the difference between this experimental and calculated magnetic moment value is because of the population of electrons at higher J levels via thermal excitation. To know more about this topic, please refer to the subject lanthanides and actinides, D and F block elements. The YouTube link for the lecture is given here. Please go ahead and watch the video. Thank you.